Yes.
Yeah, good. Okay, so I don't need to shout. That's the news. So first of all, thank you very much for inviting me to give these series of lectures in this Mixed and Numerical School for Simulations. And so I'm going to talk about cosmological simulations, from cosmological simulation to real observations, and the ins and outs of the mock world and so on. And I thought the first thing I will start with is the real universe. And one of the questions I was going to ask here before I even start is just a show of hands, who is considered here themselves as a theorist or as an observer? So theorists, hands up. Okay, good. And the observers? Yeah, okay, yeah. If encouragement is needed to figure out if you're an observer, that's good. That gives me a good reason to be here. So I'm going to be the attempted...
There's something in the middle?
There's something in the middle, so probably me and so on. Because I am neither a theorist nor an observer. But here, for this crowd, I'm going to be the pure observer. Yeah? And I usually play this dual hat role regularly. And it's actually quite important because to understand simulations, you need to understand the observations as well in order to make the comparisons and so on. So this is why I'm going to start with the real universe today. So this series of lectures has a couple of aims for the next few days. Is to introduce basic observational concepts, to provide a path on how to create fake universes, to connect real observations with simulations by a clear understanding of observational measurements. Yeah? Because I think it's very important that we don't think that something been measured, I can just reproduce and so on. You need to understand what it actually means, how it has been observed, and so on. And I take now my theory hat on, and as a theorist, we love to go to papers and pick something up, and this is the truth. I'm just going to go to this. I don't read the details of the observational paper, or even if I do that, I'm not going to speak to the colleague who did it. Because it's just going to be too complicated. He's going to talk about magnitudes and stuff like that. I don't, really care about. I want, real, physical quantities all the time. But unfortunately, you need to worry about those series. So, possible take-home message from these series of lectures is to don't forget to discuss observational data and measurements with those who gathers them, and do the analysis. Because there's a lot of things which are not written up, and they might be very subtle. They might be very obvious, depends who you are when reading it, and not everything is written down in the details. So programs for the first couple of lectures is a brief and possibly biased overview of observational cosmology, where I will consider mostly survey types and survey characteristics, including statistical properties of the surveys, because to some level that's how very much this work is going to be useful from the point of view simulation-wise, and then possibly be brief and hopefully unbiased overview of statistical descriptors for large-scale structural analysis. The one-point statistics, number count, stretches distributions, luminosity functions, stellar mass functions. They can all be covered in one slide, or they can form a whole lecture on their own right. I'm just going to find something in between. Color distributions and multi-point statistics and so on. And observational cosmology, as this first lecture is about, is and what I will consider. You can have many parts, and actually Salman did a great job to introduce the many different forms of it. And you have typically the large-scale structure studies. We have photometric spectroscopic galaxy catalogs. That is kind of like a very big avenue now, and that fits in well with Mariana's starting point of these series of lectures and so on. You have the cosmological footprint on the CMB. CMB is huge amount of information about the cosmology and so on. Cosmology with standard candles, how to extract from cosmology from supernovas and so on. I've missed lensing. That probably falls into the large-scale structure, and to some extent. I will mostly focus on large-scale structure. I will not consider CMB and cosmology with standard candles and so on in these lectures, even though they're part of observational cosmology, because I want to focus on what is more relevant for what you might be doing with respect to simulations and so on. Even though all of them are used to define your cosmology, because you want to combine the probes. So there are multiple aims on large-scale structure surveys. And if I start up from the first point is just mapping the universe using galaxies as tracers. Yeah, that is basically it. Create a map, and we have loved doing that for years and years. But that's not really scientifically interesting just to create a map. I love collecting stamps as well, but it's not very useful possibly in the scientific investigations. But mapping the universe helps us to understand the composition and the evolution of the universe. So that's now the scientific motivation for it. So we do cosmology and galaxy formation, we do surveys, and so on. Often cosmology is the main driver as a head title, but it's only recently it has been the head and actual driver of the surveys. Many surveys in the past, and I'll go over some of them, were actually mostly galaxy formation oriented. They learned about large structure and so on, but more information came about what the galaxies are and how they evolve and so on. And I think there's been a big change in mid-2000s and so on, and very much with the advent of the BAOs, the Bionic Acoustic Oscillation measurements and so on, that the design of dedicated service purely for cosmology is being done and so on. And then they can include BAOs, rich space distortions, weak lensing, probes, depends on how you're going to go ahead with it. Yeah. And so I think that's one thing we need to remember. Where is the baggage of galaxy service coming with and so on, the motivations for various peoples to do them. So I guess I should start with where it started. Is probably the CFA survey. It's really the one where everything started. It's the CFA started in 1977 actually, and that was the Davis, Hookeran, Latham, and Tonnery, and they did a 5 years work to reach in 1982 about 2,000 galaxies, and you had this Stickman diagram. It looks like it's a pie diagram where you actually show the galaxy positions here along how far away they are from us. Here is given in kilometer per second, whereas nowadays we tend to mostly do it in redshift directly. And here's functional right ascension on the sky, and it's a projection distribution. Yeah. And the nice thing with this one is that this first survey already showed that there was a lot of structures in the universe. Yeah. And you need to do these surveys to actually have this feel for this, to understand this. And this carried on afterwards. CFA2 carried on and then created until in 1995 had about 18,000 redshift. That was a very manual process of doing surveys. CFA was very manual, and the main thing you can remember from this here is this structure is huge given this area they have surveyed. And that's something which comes in regularly in large-scale structure surveys and so on, are we sampling with a volume we probe all of the structures we can see and so on. And remember, in simulations, you have an initial seed, you change it, you get a new universe. Unfortunately, we don't have this here. Well, maybe good, I don't know. Depends on which way you see it. But in the real universe, there's just one. Yeah. So you need to remember that whenever you think about analyzing any analysis. So over the years, till the mid-1990s, there was very many different surveys. Did either imaging surveys, you had APM, automatic plate machine, scanned photographic plates of the southern sky. It doesn't sound that long time ago, but CCD technology wasn't up at that time to be able to do on large scales in the mid-1990s. 2 months was a shallow near-infrared survey for the whole sky with twin telescopes. That survey is still today state-of-the-art in its regime, because there is no near-infrared survey covering the whole sky and being calibrated to that accuracy. So this is another thing one need to remember when working with surveys. There's some historical value, which is legacy, and there's some values which comes with time that you actually need to, you focus on something specific. And more and more today, we become much more science-focused to do an experiment. A bit like Salman said, many of these experiments today are becoming particle physics type experiments. Yeah. So there's this kind of two drift in the astronomy community, whether it should be more legacy value or it should be experimental stuff. And these surveys led to also to various spectroscopic surveys in the mid-1990s. And there are different numbers of them, but of the order of tens of thousands of redshifts over either a large portion of the sky or some 700 square degrees that was extremely large. You know, I do like this one. CFRS, mid-1990s, is the first exploration of the redshift 1 universe with 600 redshifts. From 600 redshift, they measured the luminosity evolution. They measured lots of things. Whereas today, it's like, oh no, I need at least 100,000 to do anything, you know. I think we need to remember what is the challenge you're starting off with and what you can do and what you can't do. It's a very different type of analysis you're working with, whether you're working with a small number or large number statistics. And this comes up all the time when you're doing surveys. So yeah, I just showed this image, and you will hopefully, if I manage tomorrow, show you the an equivalent image of the APM survey, but from a mock realization. So what this map shows, it just shows the distribution of galaxies color-coded according to their magnitudes. So in one sense, it's mainly red because it's dominated by the faint galaxies and so on. Yeah, and this was state of the art in the mid-1990s survey. And one thing I like to point out, you will see it many times, the shapes, there are holes, and so on. That's part of your survey. Yeah, that's not part of your simulation. You will need to think about that, how to do it. The 2-mass all sky survey here is an example of, again, how you can see this is in one sense, our galaxy coming in. And this is all, again, all of the infrared light in the local universe. You can see various structures coming up and so on. So these ones are extremely important to start off with, to actually have your surveys, to understand your galaxy populations in different wavelengths. Just to give you an idea that the previous one here was done in optical, in the B band. It's pretty much very star-forming galaxies, whereas this one here is in the near-infrared K band, which is much more stellar mass oriented. So you probe different physics with different wavelengths. Again, from the cosmology point of view, it doesn't matter, or shouldn't matter, because if I'm doing cosmology with one type of object or another type of object, I should find the same universe. So again, these are things we need to bear in mind. Galaxies are complicated objects, but from a cosmology point of view, you want to marginalize over it. Now, to make the big step ahead to what we have today, to be fair, I was very lucky. I just happened to be at the right place at the right time. But the big thing which happened was instrumentation. In the mid-1990s, they built on the AAT the 2DF instrument, which was revolutionary in its time, in the sense of being able to configure 400 fibers automatically on one side of the telescope while observing with 400 fibers on the other side. Yeah, and that meant that you can actually do spectroscopy, multi-object spectroscopy. Now, why do I point this out? If these technological advances hadn't happened at that time, we wouldn't be with those services we have today. There are many of the services are driving the technology, or technology is driving the service. There's a combination of things, yeah? And then you have to live with the limitation of technology to define your service as well. So there is one part in 2DF, in the sense like the instrument, and here's an example of this robot arm is actually picking up one of these prisms, which is picking off the light, so on, so you can actually have over 400 fibers picking in the light and so on. It does that. It takes an hour to configure. This configuration time led to the survey depth of this 2DF Galaxy Redshift survey, because that was the optimal way of using the telescope. So there's a lot of things which are just indirectly coming into to the limitation of your survey, or definition of your surveys, which you need to take account for. But from a theory point of view, it doesn't matter at all. But it will have now an implication on how you interpret the data. There's another view of the fiber positioner, or the fiber being put here on the telescope, so you can actually see how the fiber are picking up the light, and then the fibers bringing out the light here up to a spectrograph, and where you can get your redshifts. Now, why do I make a big fuss about this one? This was the first one which was automated. You've heard a lot about SDSS, yeah? That's manually plugged in, thousands of fibers. Cheap labor, I'm not going to say where it comes from, and so on, if it's graduate students or whatever, but it's still today manually plugged in. And they have plates and plates and plates to be just plugged in like this. Yeah. This is automated. Yeah. And this is where we go on for the next generation of object and so on. So in the mid 2000s, you have the knowledge of the low redshift universe with 2DF galaxy redshift survey that 250,000 galaxy redshift or 1,500 square degrees. So you had a good understanding now of the logical structure in the universe. Yeah. The 2-mass redshift survey got 45,000 redshift over 42,000 square degrees. It's an all-sky redshift survey. That's really hard to accomplish, to have a good knowledge of the all-sky. And SDSS, with its million redshift by 2008, over about 10,000 square degrees. Now, these ones, what is nice with these ones is this is fully automated in the sense of 2DF instrument, but manual interventions on how to decide things. The 2-mass redshift survey is fully manually done. It's actually manual to the extent that it's worrying how manually it has been done, because it's collecting single spectra here and there and so on. So it's very hard if you want to do a statistical sample out of it, understanding it. Luckily, it's rather complete. SDSS is the halfway between. It's automated in the sense of knowing what to do and so on, but is still manually plugging in the fibers and so on and all that work. But it's been great service. Now, the 2DF and SDSS, main thing from them come out in like 2005 is this BAO measurements and so on. And that was really how you started driving all of the cosmology service that we have today. Yeah. And that's the planning of future large BAO surveys and focus on rich space distortions, probes, and so on. And there's many of these surveys now, and I'm going to mention this. In the meantime, this was the low redshift universe, anything below redshift 0.3-ish. Yeah. So you have the high redshift universe, which trotted along in its own way, much more manual, and so on. And with Z Cosmos up to redshift 0.4, with a couple of tens of thousands of redshift, deep 2 as well. And those surveys are very important today to help us understand our selection effects, because they were perhaps maybe manually done, but actually you have a large sampling of all the galaxy types, or a very good attempt to do that. So this is a view of this 2-mass redshift survey. You know, previous time I showed you the picture, which was just the galaxies position. Here they have been color coded according to how far away they are from us. You know, and that's also, you can see the structures coming up and so on in here, the galaxy in the center. Now you might notice I vary randomly, like all observers love to do, the orientation of the galactic plane. Sometimes it's here, sometimes it goes like this. You just have to figure it out when you look at it. Yeah, that's just standard. But it's one of these things. Observational cosmology is observation stuff. Is just there's many ways of presenting everything. You know, it's not like standard way of doing it. And I think this is kind of like the cone diagram here. You remember the first stickman on I showed initially. This is the equivalent one for 2DF galaxy redshift survey, where the stickman probed out to this area here. Yeah, and now this was about 15 years ago now. Probed out redshift 0.2 with large distribution galaxies. Now, do you remember I mentioned the stickman was kind of large structure causing troubles in the survey, but that's just a small survey. Let's do bigger. This survey here has the same problem. Yeah. Now, 2DF wasn't as good as branding, but the structure here, the two big structures, there's two structures you can see in these surveys, and I think this is the one, yeah, this is the one, is the branded SDSS Great Wall. Yeah. And it is just a great wall. Just go through it. Yes, please.
Why, as you go farther, you see less galaxies?
Because it's flux limited. And this is where I'm going to come into the selection effects. But you're fully, so in one sense, you don't see less galaxies. You do, but you see different galaxies. They are not the same traces as function of position here. And this is the main issue with galaxy surveys. They are mostly flux limited. And therefore, all right, not an issue, but you need to account for it. Yeah. That means you need to understand what is called the selection function. All of those things I will come into during the talk, but it was very good well spotted in that sense. The other thing is, actually, if it was truly the same number density of galaxies, in this plot, you would have far more dots out here, because there's a wedge which have been collapsed down. And if you collapse the volume out there, is much larger. So if there was the same number density, it would be much, much higher. So by just giving this information out, you can see that it's pretty much volume limited out to here, or it's not exactly volume limited, but it's not far off. And then the selection function starts to go down, and you start losing galaxies. And this is just a 2-degree slice. And when you do these slices, you tend to, with more and more sampling of galaxies, you reduce the thickness of your slice to actually be able to see all of the galaxies. Because if you take all the galaxies and pressure them down, you can't see a thing at the end. So the cosmology service details here today, on the spectroscopic side today, is you have BOS and EBOS, SDSS 3 and 4, BAO and RSD with LRGs, ELGs, and quasars. So I will come in later on to talk about what LRGs, ELGs, and quasars are, but these are the tracers. Now, as I mentioned earlier on, initially galaxy surveys, we sampled the whole population, whereas these cosmological surveys, you target. You have a more targeted approach to the samples because you're after specific science questions, and therefore you have a way of optimizing your sample. Yeah? And this is what all of these objects are. Why LRGs? Because they're luminous, red galaxies, they're easy to find and detect, and so on. ELGs, they're hard to select initially, but they're really easy to get a spectra for because they have emission lines. Emission lines are features which are easy to redshift. And quasars, they're also quite easy and quite strong, but the good thing is they probe a very different redshift volume, very high redshift. You can use them for 2 purposes. But I'm not going to go into that in more detail today on that. I'll do it tomorrow. Yeah, Vipers is another survey, much lower redshift in that sense. It's a bit, not lower, it's a slightly higher redshift than BOS and EBOS, or complementary. RSD, which mainly rich space distortions with dense sampling galaxies, so that is a different way of doing it. Multiband imaging, you have DES, the dark energy surveys, which is 6,000 square degrees, mainly aimed at lensing. KIDS, 2,000 square degrees lensing. You start again, there's a zoo of surveys. Yes, there is a zoo of surveys. There is absolutely loads of surveys out there. But the combination of them and how to use them is the hard part. Yeah? And it's not going to be better or easier as time goes on. Because there's one thing we ask more and more from these surveys is higher and higher accuracy, which means it's going to be more and more important and we understand all the intrinsic details on them. You have galaxy information surveys, which I would mention, for example, GAMMA, which is a galaxy mass assembly survey, which is actually very much like the SDSS main survey, but just slightly deeper, which means that you probe fainter objects. POUNCE is a narrowband imaging survey, which just started and so on, but there's lots, and I can give you as many as you want. The reason I choose this one here as an example, Viper survey, is to show you some observational characteristics of the survey, which from a theory point of view is like, whoa, why on earth do I need to know that? But you need to know it very well in order to understand the selection function, and you need to understand how did I got the data I acquired. So first of all here, the Viper survey, what's interesting here, this is what we call a redshift distribution, redshift on the x-axis. And this plotted for 2 fields, W1 and W4. Fair enough, there are 2 fields. That's useful for testing your sample variance. Note I use the word sample variance, not cosmic variance, because cosmic variance is related to the size of your universe, not related to the size of your survey. If I point there and there, I get sample variance. Yeah? But most people call it cosmic variance, even though they're wrong. And here's the overall redshift distribution. A couple of things to note. First of all, the redshift distribution it's peaking at 0.7 or 0.8, but very few galaxies are reaching 0.4. That would not be the natural thing if you had a simple selection in your survey, if you were flux limited. And that comes into the fact that they have done a color selection. They've used magnitude R minus I and U minus G color band and selecting galaxies which you know that these objects are at higher redshift than these ones here. And you, into some level, pre-select your object to be in the redshift range of interest. Now this is great for cosmology, because that means I don't need to spend a lot of time on objects down here, which would dominate my sample in numbers, whereas I can actually focus on those I'm interested in, because this is the redshift range where I want to do my measurement, on cosmological measurement. And here to show that it is working, because those who are color selected in the blue histogram, to be below reach 0.5 gives you this distribution here. And it, it's pretty much died out at reach 0.6, and at 0.5 is not that many of them. And these ones are color selected to be above reach 0.5, and you have a bit of a tail down here. What this tells you from this diagram is tells you, because this is where they have done the full sampling of all the galaxies available, tells you that actually above 0.55 or 0.6, Vipers is actually very good to use as a complete sample in its own selection. Yeah, it's never going to be complete in the terms of being complete, but it's just, yeah, and as the word complete will need to be characterized a bit better once we come across with that one. So, but that doesn't help, 2DF and this multiplexing and so on is great, but 400 or 1,000 fibers done manually by people, or 400 fibers doesn't give you the speed you need to do the 35 million objects over a couple of years. Yeah. So you need, again, an advanced second generation multi-object spectrograph. You really need to boost up the technology. Yeah. Technology is, again, linked to what you can do. Equally much as what Salman said for computers, the simulation can do is linked to the quality of the computers. They work in parallel. And the best, honestly, the really good scientists, they know how technology is working, and therefore they can plan really well what is going to be the next generation of things. And it's amazing. It's great to see that, because they actually look at what is going to happen in germanium, for example. The CCDs in germanium are now better to do certain types of wavelength ranges. The response rate better. So that's going to help us to work in a different wavelength window. So it's knowing that. It's keeping track of those developments. So here, this is an example of a DESI petal. It's 1/10 of the full DESI focal plane, with holes here. All of these things is like holes here, is where this object here, with this DESI robot, will be positioned. Yay! DESI is going to be automated. Not going to have to work manually on figuring out where to put them in. I'm glad for that, because I felt sorry for the person who dealt with 5,000 fibers otherwise. That's a lot of work. But, and I think this is the technological thing here, it's of the order of 2-minute configuration for the 5,000 fibers, as opposed to 50 minutes for 2DF. And that is technology as well. Because it's not just to have 5,000, but you need to make it configure quickly, so that will influence now what the type of science you can do. Because if you were to observe something, let's say, and it takes you 10 minutes to observe it, to get what information you wanted, but it takes you 20 minutes to configure the field, it's not very efficient. So it's this combination of factors, how to drive it. Now, this was a constraint to put down that's because at this level, the server was designed with cosmology in mind. And therefore, they had quite precise requirement on what needs to be able to be done in order to be able to do the survey. Yeah? And so on. So just give you an idea of how big this is. This is, in reality, this distance here is 81 centimeter. Yes, so it's quite big. And you have all the different petals here. And each robot is positioned in one of the circles. And it has a way of moving around with 2 arms. So you actually can cover the whole field except where it stands itself. It can't cover back on its own position. Yeah? Limitations that need to be accounted for in the analysis. Yeah, we need to know how to deal with this. And this is what these patrol radius that they are actually covering, each position here is covering different areas and so on. All of these things, maybe at technical, not relevant point, are actually really important in analysis. And this is something I learned when working in 2DF already, because that's how you can actually make good use of the survey. And this is part of the survey systematics. So what's going to be the state of the art in 10 years' time in this level? But it's, cosmological spectroscopic surveys, which using what I call the bright traces. You have PFS, the prime focus spectrograph on Subaru. There's going to be a 4 million redshift survey between redshift 0.6 and 2.4. DESI, 35 million redshift. That's very relevant for people in here. And so on with 14,000 square degrees coverage. Euclid, kind of similar to DESI, but have different overlaps. But the main difference here is the Euclid is slightly higher redshift, focusing on slightly higher redshift for these main galaxies. But the bigger difference here is the lensing component of Euclid, of the order of 1.5 billion objects with shape and photometric redshifts. Yeah. So these are kind of like what's going to come, and there are more. There are more things coming along and so on. So the analysis just becomes more complex. You need to be able to deal with large data sets and how to mimic them. So galaxy information surveys, which is the other side of this kind of surveys, and I always keep them in parallel because they are needed for different purposes when you need to understand your selections and so on. So there will be one moons with the 50 square degree, and this is going to be very complementary for Euclid because it's going to help Euclid to understand which are the objects they don't get redshift for in which ways. Because this is going to be a near-infrared survey on an 8-meter telescope with of the order. This is very of the order, because galaxy information surveys are not very much in big numbers. So the 0.1 million could be equal to a factor of 2 off, or factor of 3 off, because they are not funded in the same ways, and so on. So it's very different. But the whole point is creating an SDSS type main survey, but a redshift 1.5. And that's going to be very useful to understand the galaxy population, but also understanding which are the objects we don't get redshift for and so on. Waves is another survey which on foremost have different components of the order of 1 million redshift again for different purposes and so on. So there's a lot of surveys coming along and so on. So in that sense, I usually tend to say that the future is bright. Yeah, and the future is very bright if you look at this graph by David Schlegel, and which actually shows the spectroscopic redshift acquisition with time. Redshift survey increasing 10 times every 10 years, tenfold every 10 years. So this log number of galaxies versus year. You start off with the famous CFA survey in Stickman with about 2,000 redshifts in the early 1980s, and goes up in the 2DF, SDSS era and the DESI era of 30 million by this. And if you carry on this graph along this line, all linear modes will be mapped by 2043. If you actually carry on the new project out here. And all the typical galaxies mapped by 2061. Good, because I'm retiring just before that, so that's not going to be worrying too much for me. Now, I don't think it's going to be an issue actually in that sense either. There's much more to come, but it's just the idea of how this has been done. And this is only thanks to instrumentation development. I think it's one need to bear that in mind, and how they have worked together with the scientists to develop them. So the types of surveys, you might have seen a couple of these ones. Cosmological spectroscopic surveys now, we mentioned that. What are they aimed to? They're large to extremely large volumes. They're bright galaxies, mainly as tracers, often strongly biased, but not always. For example, the ELGs, which we'll come back to later on, they are not that all strongly biased and live in small halos, so they're actually quite a hard tracer in that sense. But LRGs are very strong. Strong emphasis on targeting algorithm and sampling rate, making sure you get your redshift, you get your understanding of your survey. Is systematics and statistics prime reason, And it's a statistical probe, BAO and risk-based distortions, Key issues in modeling survey selection function to sub% accuracy to some level. That is really the issues. And you have lots of them here, and I'm not going to read through the list, but these are the kind of things you have, And I like this plot from the BOSS survey, DR12, and just showing where the galaxies are. This is the main, they're like LRG samples down here out to, extend. Here's the quasars, going out to much higher redshifts and so on. And they're used for very different probes and so on. And it's a nice figure here, seeing how far have they probed the universe and out to where is the CMB and so on. But then we have the imaging surveys, which are working in a different level, but they're also large, extremely large volume. All galaxies in flux limit in some bands, and that's kind of thing we're going to work a bit more on. The strong emphasis there is on the multi-wavelength, because they need reliable photometric redshifts. So they're not going to get a position through the spectra. They need to have some approximation for the positions, and that's used photometric redshifts. And I'm going to introduce that later on. The homogeneity of the imaging data set, both spatial and in its depth. That's very, very important. But that comes in even in spectroscopic surveys, because spectroscopic surveys need an imaging catalog to start off with. So it's all of these aspects we need to understand. And the prime observing conditions, which are key for lensing studies, primarily the good seeings and so on. And there's absolutely loads of those surveys and so on. Just give you one example. I like this one for the shape of the survey. This is the dark energy survey tank, I would call it. It's kind of the tiling of the survey. Now, you wonder, who on earth came up with this brilliant shape of a survey? Yeah, no theorist would. Yeah, I can guarantee that. But it's very good reasons, absolutely fantastic reasons, which, for example, here, you have very, very good data here to allow you the calibration. So that was definitely is not as visible or as good to be seen for the rest of the survey as the southern part. So you do your main part down here. This overlap with the South Pole telescope information as well. So there's a lot of constraints coming in that you have to work with, and which create your imaging surveys in different ways. And that's something I want to mention because it's important when realizing these projects. So there's a third type of galaxy survey. It's the Galaxy Information Survey. So unlike the two previous ones, it's really working on high signal noise spectroscopy, including spectral flux calibration. So actually can actually use a spectrum to get derived properties, physical properties from. Multi-wavelength coverage, because again, they want now, not for the photomagnetic redshift information, but it's because they want to address different physical processes and different wavelengths. So that's the motivation has changed to why you need it and so on. Large enough volume, but to sample all environments well, put all these words in kind of like quote because there's no real definition on what is all and well. It's the typical related to an instrumentation limitation that you could not put two fibers too close to each other, even though you put them in manually on the focal plane. It's just the spacing, 55 arc seconds. You're like, does that matter? It does if you study groups and so on. It has a huge impact in small scales. So that's one of the things which is actually how you see instrumentation coming back to you again. Gamma main sample, spectral flux calibration for spectra is not good at all. And so here, it's just a zoom into the structure estimate. Great wall here coming out. And here they've been color coded out according to the dots are color galaxies as function of red, and here the redshift is here. Yeah. So you can see that red galaxies predominantly live in the biggest clusters isolated and so on. So that gives you information about the galaxy process. In the case of galaxy in gamma, the focus was on the multi-wavelength aspect. So having galaxy information for the UV, optical from VST and SDSS, near-infrared from VISTA and UCURT, spectra from the AT. The WISE instrument gives you the mid-infrared, the far-infrared information. ASCAP, which still is on its way to be built, information. And GMRT is some longer wavelength information. This is rather unique to collect all of this information in one patch. It's very hard work to get this information in. But that becomes the strength of that type of survey because it can actually analyze information purposes. If you look at how these surveys compare in terms of redshift, this is clearly a propaganda plot because it's been plotted such a way that gamma looks its best. Yeah, now it's no connection to the fact that I'm part of gamma and so on. But the point you want to take out from this is different surveys cover different regions of the sky to different depth, sampling the galaxy population differently, so and more or less in detail. So in these plots, when you do it, again, this is RA, and all the declination has been hemisphere. In the center, you have this one here is SDSS DR9, the blue one there. So it gives you an idea of where these surveys are, and this is a good plot to actually compare surveys in terms of the density of spectra and the area of them. You have the surveys which are lining up on these lines of 1,000 redshift, and you have the million redshift surveys out here. And the difference here we need to remember is some surveys have been selected in different wavelength, but some surveys are magnitude limited, meaning flux limited. Some surveys has only photometric redshift information. Some are highly targeted. So you can put your plots, your diagram up and tell you the method of how good it is in one way or another. And this was done for the wave surveys. So that's why you can see the boxes being put around and how they open up the new area here. If you want to put in DESI here, DESI is very large out here, and it has but it doesn't have a huge number density of object per square degree. It's over the order here, but it has absolute loads of galaxies. But the aim is different. It depends whether you are cosmology oriented or galaxy formation. Anyway, this is the volume we have sampled so far for BOSS. Yeah, ignoring the what's it called, the quasars. And you can see there's quite a lot left over. If this is redshift 1, 2, 3, and so on, you go out in the whole universe. It's quite large volume left over. And this number of modes we have sampled, if you want to look at the modes in K perpendicular or K parallel space, and this is what you've sampled so far in BOSS. There's still quite a lot of modes left over to work with, and which is why you can still design new surveys to do better results at higher redshifts. But at low redshift, pretty much all of the modes have been sampled already. So it's going to be hard to do much, much better. Now, having done this, you have survey characteristic, basic survey characteristic, number of galaxies, area, effective area, flux, limited, target selection, redshift range, lots of decent things. The advanced characteristic I would call, selection function, angular and radial, underlying galaxy population is what's the luminosity function, stellar mass function. The clustering properties as well, which is important. And you can be either angular or 3D and different statistics considered. And these are the ways you tend to characterize statistically your sample of galaxies from your survey. So now why this is relevant here is because this is how you tend to, when you create a mock survey, you need to mimic as many of these properties as possible, or your aim is to mimic as many of these properties as possible. And which one to choose depends on your science goals. Yeah. So, why do survey characteristics matter? That all survey have inherent selection effects, flux mimicked, means a lot volume limited. Your simulation is 99% of the time volume limited, unless you do zoom simulations, in which case it's a bit different. Completeness, not everything that could be seen is included. Yeah. So that's another thing is it a completeness due to the fact that I didn't decide to target them because there was no point in targeting them? Or is it completeness that I couldn't target them because I didn't know they were there? Instead my input catalog was incomplete, and all of these things need to be mimicked to some level, because if you want to do a simulation, going from a simulation to observations, you need to know what the limitations are, because your perfect mock will not look like the real data. Not just because you don't know how the real universe works, but also because you don't understand the limitation of your data. So therefore you need to know both aspects of it. Numerical simulation have inherent limitations as well. Spatial and temporal resolutions, numerical accuracy, the physics implemented, and so on and so on. Same thing. There's no difference. We should just make sure that everything is spelled out clearly, and so on. And that you need to do in order to make a simulation observation comparison. And this is where I'm again going to drag in the word speak to your colleagues, speak to those who do it, because what's released, what's given, and you can grab, doesn't give you all the information usually. It gives you good little amount of information, but not everything. And that's where, and depending on the project you're working on, people might not have written up, by the way, don't use this data set for this. But, because it was one very small case scenario. Yeah. But that's very often the case, that if you speak to the people who did it, they will know whether it's good or not. So which survey characteristic matter? Depends on specific science goals and the legacy value of the survey. So you're going to mention this part of the SDSS, for example, 99% or even higher redshift completeness overall, but only 60-70% complete for galaxies with neighbors within 50 or 55 arcsecond of each other. Yeah. So first of this is great, fantastic survey, I can use it. The second impacts strongly on the analysis requiring small-scale information. So these are things one need to bear in mind. Yeah. So gamma, for example, addresses the second issue, but it's only over 200 square degrees. So it's tiny survey in that sense. Yeah. SS imaging is generally very complete, except for low surface brightness galaxies. Fine again for cosmology studies. we don't care about low surface brightening galaxies because the galaxies we're going after are intrinsically bright objects. But needs to be accounted for in galaxy information studies. Yeah. So again, you need to understand the limitation of it. So this, I gave a couple of slides here. I thought it was funny just to see many options on the sky coverage until reality kicks in. So this is how the SDSS3 data release 9 look like with the different surveys. Now, this looks particularly bad because it's a combination of 3 surveys, Legacy, BOSS, and Segway 1 and 2. Yeah? But it gives you an idea that the survey footprint is not what you would have imagined. This, I think, is beautiful. This is really great. No, because it's extremely rare. You see something final, which is so complete, so uniform. You know, sorry, there's like 2 patches here, which might not be ideal, but honestly, it looks really good. And look at the completeness scales. They haven't tried to hide it in the numbers, because it's very easy to make a nice plot, plotting from 0 to 1, and you don't see the scale. This is from 0.7 to 1, and nearly everything is between 0.9 and 1. So it's beautiful. But this is extremely rare. So one should, you know, when we work with great data sets, one thinks, oh, it's always going to be like this. No. You know, it's just going to be hard to make sure. This is very rare, and that's why it's beautiful in that sense. It can be complicated for other reasons. This is the DESI footprint. Now, what's complicated here? This imaging comes from BAS MZLS. This imaging comes from decals. This imaging comes from decals plus. This imaging comes from DES. Why? There's 2 hemispheres. We have telescopes that can't reach this high up because decals is done with decam, which is in the south. So you need to worry about these things when you do the imaging. SDSS, again, same telescope, same thing. You know, this is another problem. This is another thing. This is the Euclid sky coverage. Now, this color coding here is more related to when the data was acquired or will be acquired. This is a plan. They have lots of plans. I'm not going to go into this series of plans. But you have some interesting features coming in. You have one patch here. You have this patch there, which connects with this one. You have this long patch here. You have this patch here. So basically, you have 1, 2, 3, 4 patches. When you have surveys with 4 patches, you need to worry about calibration in the 4 patches. You know, calibration is really hard, especially when they don't join up. One of the reasons why DES did this kind of like cannon footprint or tank footprint and so on. So the basic, you know, reason behind those crazy survey selection functions is basic observational astronomy concepts. The Earth rotation axis is inclined with respect to orbits around the Sun. Nothing new to you, I'm sure. I hope not. You know, not all sky positions are available any time. Yeah, observing seasons are influenced by weather, length of night, location of telescope, all basic stuff. But you can't get away from them. Yeah, and that's the thing. The moon rotates around the Earth. Yes, no news there. The brightness of the sky varies with time. Yeah, we knew that as well. And affects bluer wavelength more. Again, things like that need to be tracked. You know, so all of these basic stuff. We live in the Milky Way. Not all part of the sky observation statistical equivalent for exogalactic studies because you have a galactic plane coming in. Yeah, time allocation constraint, and this is where the politics comes in natural sciences. So first of all, not all sky positions have equal observing pressure on them, so you can't get anywhere in the sky equally often, and so on. Location of telescope and instruments, but also it would be good that we also did this. Okay, we're forced to do this now because they tell us to do it. So there are combination of mergers and so on. So there's lots of interesting things. So I'll just give you an example of gamma. We have 3 fields in the north. Not because we wanted 3 fields, because the allocation we're given more time than we wanted in a given year, but less overall time that we wanted. So you're stuck with that. So you have to deal with these things. And for space mission, you think, well, that shouldn't be a problem. Yep. Euclid had it because you have ecliptic coming in the way. They don't want to observe in the ecliptic because that's not in the ecliptic plane is really hard for Euclid to work. You know, you can't get the same calibration qualities. So all of these things comes up, you know, and then they come in with the limitation of the observing that you need to survey conduct over a period of time. Yeah, so it means that the variability of the observing conditions comes in. With time, the hourly, nightly, weekly, monthly, yearly changes. Yeah, seeing depth and filter response sensitive to observing conditions. Manual interventions, these are the best ones. They are untractable. unless they write them down clearly everywhere. But this is, we thought it was a good idea to do this. Thank you. It's never a good idea, usually if you're not, Minor interventions is the one thing you really want to go away from. Changes, in the observing strategy is a pain to model. I think in this case, Boss had that initially, if I remember right, but they managed to get away with it because they had enough time to actually go back and do the work. But if you're lucky enough, you can do it, but it's really hard. And modeling this is terrible afterwards because you don't want to model the probability of observing an object up on the position there because it was Thursday afternoon or in the start of the survey. You can't do that, But these are the things you have to worry about otherwise if you have these things. Instrument performance, telescope orientation, wavelength, upgrade maintenance, that's coming in. All of this has an impact on your survey strategies and so on. The variable in input catalog, imaging homogeneity, calibration, star galaxy separation. There's a lot of these small things coming in and so on. And I think I will can do this one as well, and then I will stop. And the other thing is, last thing I want to mention here, the classic observable is the flux and magnitude definitions, which nobody wants to deal with. I'm pretty sure even observers don't want to deal with them because it's a pain. There are equally many definitions as you can imagine users. Not exactly, not far off to be fair now. So observationally, there's a large number of ways to measure the flux, or magnitude, which is minus 2.5 log 10 of the flux, plus a constant. Volumetric, which is pretty much everything, Fine, that's impossible to do, because you can't get all of it for all the spectrum, the whole spectrum. That's impossible. Fine, so let's ignore that. Total, that would be great. Get all of the flux within the bandwidth of a filter, which have been received from the object, Now, all is a problem because though we can receive all of those we have received, but we don't know all those which we were supposed to have received. And that's the problem of it. And then on top of that is, how do you measure that, So they are actually realistically not possible. So for extended object like galaxies, we resort to a series of definitions. Aperture fluxes, fiber fluxes, PSF fluxes, Petrosian fluxes, model magnitudes, searching magnitudes, 3-cell mole dots. And honestly, you can do a whole lecture just on this. And I'm not going to do that. I just list them up for you to be aware of that there is absolutely loads of magnitudes, like definitions on top of filters and so on, which all comes with its quirks and its benefits. And the science goal ought to define what you want. But it's not really true, because quite often it's data availability or data reduction feasibility will lead to what is being used. So it's like there's some mix mash of constraints and so on. But this is what you have to deal with. In your simulation, do you think you predict aperture, fiber, PSF, Petrosian, model, Searsic fluxes? No, clearly not. Ooh, that's going to be a problem. So I think I will stop here. Can I let me just see here 2 seconds. Now go back. So I'll stop here and I'll take small break 5 minutes. And small break 5 minutes now. Just.
So clearly, if you don't actually know about the actual methodologies and the nitpicky quirks of how things were carried out, you will have a bad time. Right?
Or you will not focus on the right things. That's the problem,
Or you will waste time.
You will waste time,
So
you need to, this again, why it's become that, I rejoin the point of Salman saying that it becomes more and more important to know the whole breadth.
Yes, and so in order to ameliorate that, you should really try and contact the people that actually set up the experiment.
Yes.
Okay.
Again.
So basically the solution is we should go for more beers and talk to these people and read their stuff. But after, like, what if you don't have access to them, or?
No, so the thing is, so the one thing you have to do more is the fact of, so first clearly is talking to them, but also by talking to them, they will guide you very much quicker what to do. You don't need to know the ins and outs. I honestly, if you put me on the spot, what's a pertussis magnitude? I will read it off to you and so on. No, I would not know it. But the fact that I'm aware of it makes me sufficiently knowledgeable to know that I need to worry about it. I need to ask that relevant question. It's kind of like, I don't run simulations, yeah, but I need to know what are the basic limitations of simulation to some level without having to run them. That is the knowledge you need to know. And when you see something like, could this be an issue? You can ask that question because you know what's around, as opposed to, you don't need to solve it. You don't, somebody else will tell you how to deal with it and what it should be, how to deal with it and so on. But it's just that's, what is comparable? Can I just take these two things together and so on? Because I'm not asking anybody to be specialists in everything, but it's impossible. But you need to be, and I think it's more the awareness factor in that respect. Yeah, you're welcome.
So, is there any other question? If not, you have 5 minutes. No?
Yes.
It's time to need now. Because when
Okay, let's restart. Okay, so I'm just going to carry on for a couple of more minutes here. Another thing which is need to think about is the dust extinction when the observations. Yeah, that's another observational effect. That the sky is not uniformly transparent everywhere. In one sense, there's dust extinction in the sky. Clearly, in our simulation, we have that as well. I'm joking here. And and the thing is also the fact that dust extinction is wavelength dependent as well, and that you need to care about when you do these observational information. So you need to worry about these things. This is just a map of the Schlegel-Tal dust map using IRIS and Kobe-Darber data, which shows you dust extinction, primarily a lot of extinction here in galactic plane. But you can see how non-uniform it is, and how much you need to worry about this, or like take this into account when doing your analysis. Now, I'll show you how this can come across in a very obvious way, and then you can see how it becomes more complicated. So I mentioned earlier on the word selection functions. Selection functions is a survey characteristic, which is encapsulates to some extent the information or the probability that an object can be detected. Yeah? And the selection function, like the survey, is defined by the survey area, magnetic flux choices, flux limits, and so on, and various maps. Yeah? And may or may not be needed, they need to be combined and so on, but you need to be aware of them to be able to use the analysis. And this becomes where you actually, as somebody analyzing the data, you need to worry about these things and so on. So you have the imaging completeness maps, including bright object mask. For example, is the imaging complete? Is my imaging able to detect all the objects which should have been there in ideal conditions and so on? Imaging depth maps. In one sense, is the imaging sufficiently deep everywhere? Now, very often this is not needed when you have an imaging survey which is far deeper than your requirements for the spectroscopy, for example. So going back to SDSS main survey again doesn't need to worry at all that the imaging of SDSS is inhomogeneous at the 21st magnitude, because it's a 17 or 18 magnitude bright survey. So it's far beyond those limits. But if you work with the survey or the information as such to the whole depth, you can do this very quick way. You can see the scanning of SDSS camera, how it scanned the sky, in which condition it was at which nights, because it comes into the imprint on the survey. So that matters at some level when you need it. And that, again, will not come up unless you actually test the data properly. Spectroscopic completeness maps, angular map and radial distribution can be separately, most common situation. Sometimes you need to do a 3D completeness distribution in angular and radial bins. That's much, much harder. So Euclid, in the case of Euclid, it's going to be guaranteed that this needs to be done, because it's going to be actually very hard to figure out whether the probability of finding an object is on a given position in the sky just depends on that position and its flux, but that's going to depend on its redshift. But this is also going to be likely true for DESI, because there are regimes, redshift regimes, where it's more or less likely to detect an object and so on. So this becomes more complicated to model. Yeah, and you can just carry on this. So I give this as an example, because this was kind of like one of the first surveys where this became apparent, mostly because of lack of work before the survey started. So in the case 2DF, this is imaging depth maps, and I like showing them because we didn't know the survey looked like this, that this area here, for example, was only 18.7 magnitude deep, and this area here was 19.6, when we thought our survey was to 19.45 everywhere. And yeah, you learn it the hard way. And how do you learn the hard way is you actually start analyzing data, you split it up, and you realize there's some inconsistencies about. And you realize that here, these patches. So after the fact, once the survey was finished, it was dead easy to create these maps, knowing everything. But you can create these things by just in this case was an issue of calibration of the plates. You know, photographic plates, the calibration wasn't good enough, and it comes out at very obvious ways, yeah, and so on. But you could see this on the luminosity function you derived and so on. Yeah, this is a classic example of imaging depth maps to some level. Spectroscopic completeness, again, this is where, these maps really show how good you are at characterizing the completeness of your survey as a function of position in the sky. And this is kind of like quite clear in this way. Yeah, for different fields. And you have something more complicated, which can be magnitude-dependent spectroscopic completeness. And you calibrate you have a measurement of a variable, in this case called mu, which gives you an idea of how likely it is to get a redshift for an object depending on its magnitude and so on. And you can see that this varies quite a lot across the survey, and you need to account for that in order to do the measurements in accurate enough mode. Now, this was the era of easy work. This was easy in those days because the calibrations were so vastly off that it was easy to detect. Whereas if you're working on sub-percent cosmology probes, you won't be able to do maps of this kind to actually see this is clearly off by 0.2 magnitudes. No, things will be off by 0.001 or less than that. And that's going to be very hard to see. So you won't be able to see it. So you need to have methods to detect these things and splitting up the surveys. So when doing flux emitter surveys, one of the classic things, you have done your modeling or selection function and so on, but this is a classic quantity we call the number counts. Now, this is shown in the U-band in this case. This shows you the number of galaxies per square degree as a function of U-band magnitudes, and it shows you what different survey finds. Now, why they show this is because this is an observationally very straightforward or approximately straightforward plot to do, but this is something you should be able to calibrate your mock against, this quantity, because it's an observable which doesn't depend on your cosmology. Because apparent magnitude doesn't depend on your cosmology. It is what it is. My flux have received, and the number of objects per square degree, I think we can count. So that doesn't depend either on cosmology. So you'll be able to reproduce this in your mock is actually very useful. You can do this for different survey, for different wavelengths, and you can see that the number counts are not always the same. They're actually changing. And the fact that they're changing their slopes is again related to the galaxy evolution of the properties and so on. Now, there's a lot of data points here and so on, and different surveys have done different things. And in the end, why there's various reasons for the scatter. They're not always agreeing. There's one of them is sample variance, the fact that the surveys are too small and so on. But the other thing is also magnitude definitions. They're not exactly here all identical in all cases. And remember, these plots are great to show how good you're doing because they are log scales and they're showing like 4, 5, 6, 7 order magnitudes. So it's very easy to show that you're roughly ballparkish. But you actually, in you creating your mock survey, you want to show this and to subtract the Euclidean slope to some level, or simply subtract the main trend to see how well are you doing mapping this. Because you would want to make sure that your understanding is much better than the 10% level. And in doing these type of plots, the number counts is number count of extragalactic objects, hence galaxies, not stars. Yeah. Stars, unfortunately, comes into this issue, and that's where we have to worry about star-galaxy separation. So star-galaxy separation is easy in principle. Yeah, it's either a star or a galaxy. I think we can all agree on this one. But it's really hard because it depends on the information at hand and the purpose you want to use for it. Yeah. So useful information is multiband photometry. Stars and galaxies do not always reside in the same color magnitude plane or color magnitude planes and so on. Yeah. They sample a sample of high quality data, for example HST, with which you can train against is also very useful because HST has much better understanding of photometry and imaging conditions. So in that sense, you can actually do very reliably classify objects as stars or galaxies. Yeah. And also the high quality imaging enables you morphological discriminators. And there is a whole zoo, again, of method of how to do star-galaxy separation. Again, like previously with the magnitudes, there's no point in knowing them all. Different people use different characteristics and so on, but they will have different impacts on your survey properties, and that's why you need to be aware of them and so on, and knowing their limitations. Main thing is, it's essential that your survey has a uniform way of dealing with it, so that something which has been classified in this part of the survey as a galaxy is equally likely to be classified in this part of the survey as a galaxy. Now, that requires your homogeneity of your data and all your homogeneity of your data sets as well. And that's the hard part. So the key points is really to define what fraction of interlopers is acceptable. And here I use the word interlopers because, for example, of DESI, some people call a star an interloper, the majority, but some people actually call the galaxies interlopers, those who are interested in the Milky Way survey. They want their stars. So, some people's unwanted stuff is some other people's main thing. So you need to be aware of that. Yeah. And understand the quality of star galaxy separation as a function of magnitude, but also position within the survey. Stellar density is not uniform. Yeah. In high precision measurements, you will suddenly realize that actually, hang on a minute, I start observing more stars here. Why? Is that due to the fact that there are more stars, or is it due to the fact that my star galaxy separation is less good, and so on? I should deal with it. That can have statistical or systematic influences on your results, and this is something when people definitely in the BOSS community are working a lot with and mapping out and modeling around and so on. Here comes the issue with flux emitting surveys that we had before. Yeah, you have the N of Z. Typically, the redshift distribution looks like this. Yeah, so I've taken this example from 2DF Galaxy redshift survey for two reasons. First of all, you have two regions, which I like. Always, it was nice to show that you have two different areas, and they are statistically equivalent apparently. And if I look at this one has very much more spikes than this one, but this is part of the logical structure. Now, if you do a very large survey, you don't have those problems. Yeah, usually you sample them well enough. But the main issue here is to figure out how well are you able to model a selection function. Yeah, and that is actually a very, very key part in this knowing what is the mean density in your survey. Not the mean density in your survey, but the mean density, the intrinsic mean density. Yeah, and that matters for clustering statistics and so on. And that's what this solid line is shown as. Yeah, and here the other lines here are showing the scatter from our mocks that we constructed for in this case, and showing that we expect this type of scatter when we have mocks and so on. And this full survey here tells you there's a massive structure out here. Yeah. Now, massive structure at the redshift 0.25, is not this Great Wall or something like that. This is a big structure which comes up. Either is a structure or is something you haven't understood in your selection function. So you need to choose a camp at one stage in your analysis world and so on. And it's always very worrying when some of these things can seem to disappear when you actually limit to a brighter subset and so on. You might think, have I modeled this well enough and so on? Is there some systematic in my analysis that I don't know about? Is there a probability of not being able to measure redshift equally well at higher redshift than I had assumed beforehand in your best knowledge of your modeling? So these are things you need to always bear in mind. Now, I give an example here of SPEC-Z and photomag redshift distribution. So this is the case of gamma. You have a very spiky distribution, is the black in gamma. The reason spike is because it's a much smaller survey, so nothing surprising there. But the one thing I want to show here is, in this case, we have actually created a photomag redshift N of Z, which is the red one. It doesn't seem to match at all the overall one. That's the first point. We have the whole data set. We calibrate photomag redshift knowing the whole data set. We ought to get the right answer out. Yeah, that's because when plotting here the photomag redshift, we haven't plotted what we call the actual photomag redshift with its uncertainties. So if we did colorization of photomag redshifts with the uncertainties that we can actually know from the colors of the galaxies, in this case, that we have, redder galaxies might be easier to get a good photomag redshift on than bluer galaxies. When you account for that, you actually get the multicolorization of photomag redshifts, gives you this green diagram, which is perfectly nicely matched. And that tells you that, again, that you need to worry about how you propagate errors and so on in your modeling and selection functions. So now, why did I do this? I have a spectroscopic survey. Why would I want to care about the modeling of the photomag redshifts for gamma? Because I can now take the same imaging of gamma, which is SDSS imaging, and do photomag redshift for all of SDSS, because I know how to do it. So this is an example of where a good training sample can lead you to how to apply to another survey. So in these two plots, redshift distributions, and this is my last slide on this before we go into intrinsic properties. I'm gonna stop here today with the empirical stuff. And it's the modeling of the radial selection functions. And that's critical in creating a survey that you can actually analyze. Because your survey is flux limited, you need to understand what the probability is to observe an object as function of redshift. So there's two ways. There's empirical modeling. You fit a smooth curve to the observed n of z, which is, not bad, and it's certainly very quick. Or convolve the observed n of z with a smooth filter, kind of similar, Both of these options have some good trends in it. Let's look at the intrinsic modeling. The intrinsic modeling actually requires you to understand more the galaxy properties of your survey. So that can be interesting if you're doing galaxy formation survey. And there you can actually estimate the galaxy luminosity function and infer from the luminosity function the smooth n of z from it. If you do a good job, they should match up. If you do a bad job, you know that something is wrong. Either you have systematics not accounted for, or you have assumptions not properly implemented, or there are systematics you don't understand. Or you can estimate the joint density luminosity function distribution, marginalize over luminosity function. It says Cole et al. did in 2010 to 11. So both of these ones are much more complicated methods, but they are very rewarding in terms of science you get out from it afterwards, because you actually have an understanding of what the population is. The pros and cons is empirical modeling cannot account for fluctuation on scales larger than the survey. Clearly, if your survey is in a patch of sky which is 10% underdense, your modeling will be, by construction, 10% underdense. You can't know that. If there are fluctuation on scales which are larger than this, you won't be able to account for it. That is always the issue with empirical modelings. And you don't need to do many simulations to realize that it's always a problem. Unless you are coming up to the size of the cosmic variance, in the case of you actually sample the whole universe available to you. There's not much you can do about that one. Intrinsic modeling might require the modeling of the evolution of the galaxy population, and that's really hard. How galaxies evolve and so on. But you most likely need to require it unless you are on a very limited redshift range. The empirical modeling is very fast and easy to implement, but requires to be redone and retuned for each subsample, unlike intrinsic modeling. So if you do the modeling for one sample, and you do the modeling again for another sample, but actually now you have two ways of modeling. Are they compatible with each other, and so on? You need to worry about that. Whereas if you have an intrinsic way of doing it, you actually can say how it should work for different samples. And that becomes very strong, especially when you want to understand relative contribution of different galaxy samples. Intrinsic modeling requires all assumptions to be spelled out. I usually like that, because that means that you know what you're assuming, and you make it clear. And that will also lead to a better understanding of the survey limitations, because you have included, you have said why you included and so on. Ideally, you should use both approaches, because there's always two methods to do the same work. They should agree in the end of the day, or there should be a reason why they don't agree, and that's, I think, is the way forward. And I will stop here, because tomorrow we'll do more the intrinsic properties. I thought this was the best way to stop at doing empirical stuff. So if you have any questions.
Sorry,
Yep.
Sorry, the slide before this one, there was a fitting of a Monte Carlo simulation to actual operation. I didn't get the point.
No. So here so the n of z is real data. The red curve is a photometric redshifts estimated for that data set. The Monte Carlo is a Monte Carlo realization of those photometric redshifts. So the photometric redshift comes with some error. That we know are going to be better for red galaxies and worse for blue galaxies. We know how to calibrate that. So if I include that in my Monte Carlo realization of my photometric redshift, instead of saying a galaxy just has a number but has actually a distribution associated with it, then I get the green distribution. So it is, all of these ones are data. There's not like, it's just like this one here is the most, it's very rare that you see a data set coming with the distribution. That the probability of this object to have a redshift is the whole distribution. And that's very important for forming redshifts because they are not intrinsically easy numbers in small uncertainties. They are large. And you can see what the impact is because you actually moved the red curve to the green. It's a huge change, actually.
Another question.
Yep.
Just another, to clarify.
Yeah.
I know you said it. The Vicky line, black line is because...
Oh, because it's a small survey, it's a lot of structures. So in each here is actually large-scale structure. It is actually real clusters and so on. And the fact it's so peaky is because it's only 200 square degrees, as opposed to SDSS is like 10,000 square degrees. So you gain in that. Yeah. If you want, you can go back to one of my redshift cones and just decide, do I look over a small area or a large area? And you can see how much more structures you see in a small area.
One last question. No more questions. So, thanks again.
What?
The same thing.
Yes, for once. Do you need this one?
No, I
And
just,
you need the microphone.
Yes. Yeah, he needs it. Here.
I took this and then. Thank you.
Sorry.
So, is Baojiu Li? Baojiu Li?
can't see.
Is there
This one?
no, there's one place there.
Is this one? Is that right? No, sorry.
No, I
can't see it.
I can do it. Let me check. The mouse is there. It's going. It's there.
This one.
Oh, our next speaker is Baojiu Li, I think. And yeah, he's going to talk about non-standard models. So,
Thanks very much.
thanks.
Can you hear me?
Yes.
Great. Good. So, at the beginning of Peter's talk, he asked people to raise hand if they thought they were theorists, and I raised my hand without hesitation. So I'm a theorist. And as a warning, my talk will be containing fewer fancy and colorful pictures, but more sketchy ones. So I hope that this will not give you an impression that theoretical topics are less fancy, colorful. Just a little bit of context. So in this lecture series, we're talking about non-standard models to explain the cosmic acceleration. In Solom's talk, he mentioned that we have a very successful model, the standard cosmological model, which is lambda CDM, and this model has only 6 parameters. And with these 6 parameters, we can explain a lot of things from the beginning of the universe, like the Big Bang nucleosynthesis, to today, from the very large scales, like the hyper expansion of the universe, to the formation of large-scale structure in the galaxies. So this model has been very successful, and the question would be, if it is so successful, why would we want to learn other models, non-standard models? And there's no doubt that given this recent and fast progress in observation techniques, in a few years' time, we'll be able to constrain those 6 cosmological parameters with even higher accuracy. Like in 2061, I imagine that we'll have very, very accurate determinations of those cosmological parameters. But if those observing the surveys can only tell us more and more accurate cosmological parameters, I would be very extremely disappointed by that. Indeed, I would like to use those cosmological surveys to understand what is the fundamental nature of the cosmic acceleration. And this lambda CDM model doesn't explain that. So lambda is just an input from some external expert. It's like a cosmological constant. Well, it's very simple, and that is probably one reason why this model is so popular, so that it is the standard model. But there are other models, as I will discuss below. So in these 4 lectures, I will give you a brief overview of some of the most widely used tools or methods to test those non-standard models against observations. And to put that into context, in the first lecture, I give a very brief overview of the theoretical possibilities, of some of the theoretical possibilities to explain the cosmic acceleration, which is non-lambda CDM. And so I'm not going to give a very detailed review of all the non-standard models. Instead, I want just to give you enough information to appreciate the diversity of models, the basic logic of how this huge number of models can be studied and tested, and what we need to do to test those models. And in the next 3 lectures, I'll be concentrating on the more technical aspects and how observations have so far been used to test these models. So I don't think I need to talk too much about this. We all know that the cosmic acceleration is something that is very, very difficult to explain theoretically. We have a cosmological constant model, but nobody knows what is the origin of the cosmological constant, and that kind of things. And in the next few years, there will be exciting galaxy surveys, cluster surveys, such as DESI, Euclid, LSST, Eurosita. These kind of surveys will help us to more fundamentally understand the nature of this cosmic acceleration. So what we have now is a cosmological model, and this cosmological model is built up on a standard theory of gravity, which is general relativity. Here I'm showing the equation of general relativity, and as we all know, on the left-hand side you have the Einstein tensor, which tells you the curvature of the universe. On the right-hand side you have all the matter terms, and before the discovery of cosmic acceleration, people believed that these terms contain normal matter plus dark matter, nothing else. And if you apply this Einstein equation to a background Friedman universe, then you get 2 equations which govern the dynamical expansion of the universe. And these are the first and second Friedman equations. The first one tells you how fast the universe expands given the energy contained inside it. And the second equation tells you what is the acceleration rate of the expansion. And you can see that this A double dot is the acceleration of the universe. If it is positive, the universe is accelerating. Otherwise, it is decelerating. The thing is that since about 20 years ago, various observations have confirmed to various degrees that actually we have A double dot larger than 0. And that means that the expansion of the universe is accelerating. And the unfortunate fact is that this cannot be explained by this Friedman equation if you assume only normal matter. Because you see, on the right-hand side, you have the energy density and the pressure of normal matter, and both are positive. As a result, you will not get a positive A double dot in this equation. That is why we need to think of ways to extend this framework to explain observations. So there are various possibilities where the previous cosmological model was wrong, because it couldn't explain observations. And from a very fundamental level, it could be that we are interpreting the observational data incorrectly. And this is not a very popular possibility, of course, but I wouldn't rule out it. For example, one of the earliest evidences of the cosmic acceleration is that distant supernovae, if you look at them, they are dimmer, of course, because they are further from us. But there's an extra dimming, which is currently because it's believed because of the universe acceleration, expansion is accelerating. But there's one possibility, and that is if, okay, so this supernova stuff, it depends on the assumption that supernova, type 1a supernovae, are standard candles. So that means that their intrinsic luminosity is constant in time. But if this is not true, let's say if you go back in time, supernovae were intrinsically less luminous, then that could, in principle, explain this observation without having any actual acceleration of the universe. And that is just one possibility, but I wouldn't give it too much emphasis because the fact that the acceleration is supported by various observations means that it is very difficult to design a model that says that there's no acceleration at all. There are other possibilities. So we have seen that this model was built up on general relativity plus normal matter. So we can imagine that if we have, in addition to normal matter, some exotic matter, new matter, and this is what people call dark energy. And this dark energy could have some special property which makes sure that this whole thing becomes positive. And that is one possibility. Another possibility is that probably the left-hand side of the Einstein equation is incomplete. I wouldn't call it wrong, but it's possible that on very large scales, what we know, what we have tested on small scales may not apply. If you remember, GR has so far been tested only on small systems like the solar system. So it's not guaranteed that on large scales it should still look like this. A final possibility is that when we move from the Einstein equation to the Friedmann equation, we have made certain simplifications. We have assumed that on large scales, the universe is homogeneous and isotropic, and you have neglected any effect caused by the inhomogeneity in the matter density field. And that, in principle, can affect how you go from the Einstein equation to the Friedmann equation. So this is what people call back reaction, and those back reaction terms could be added to the Friedmann equations, and those can cause what we see as a cosmic acceleration. So in this talk, I will concentrate on these two possibilities, because this research in this and these possibilities are still not very active. So a cosmological constant is one of the most special possibilities. It actually belongs to this class of models, dark energy. And it is special because it is a constant. Its energy density doesn't depend on time. So the universe expands, but density of this cosmological constant remains the same. And also, as the universe expands, we have seen that matter can cluster and form the large scale structure that we see today. But this cosmological constant, it doesn't cluster. Its energy density remains smooth, homogeneous across the whole universe. And because of this, the single effect that it has is to change the expansion rate of the universe. And it's very simple. And that is why it is so popular. But simplicity doesn't mean that it is necessarily correct. And from a theoretical point of view, it is very difficult to explain why we have such a cosmological constant. I mean, we can have cosmological constants which are, for example, quantum fluctuations from quantum field theory. And if you look at these fluctuations statistically, they could behave like a cosmological constant. But predictions like this are often much, much higher than the value that is required to explain the cosmic acceleration. And it is very unsatisfactory. So what people have assumed is that there is some special mechanism which means that there's a cancellation between different stuff, so that this vacuum energy, cosmological constant generated by the quantum field theory fluctuation vanishes exactly. And there's another yet unknown mechanism that generates a small cosmological constant again. But this is still just a hypothesis which is not confirmed. And there are other possibilities, like we live in a multiverse, like there are different patches of the universe. We just live in one of these. So these different patches have different values of cosmological constant, and we happen to live in one patch that has this value. Because if we live in a patch with a cosmological constant value that is very large, then the universe would have expanded too fast, and galaxies wouldn't have formed, so people wouldn't exist, and this kind of stuff. But so far, there's no theoretical proof that cosmological constant is the correct answer. And that is why people have, over the past 10 years or so, looked at various possibilities. These are alternative models. I'm giving this picture not to ask you to read the details. This is just a very simplified summary of different non-standard models. This is very incomplete. If you look at the whole picture, it will be much more complicated. And the point I want to make is that there are so many alternative models if we decide that we want to go beyond lambda CDM. And as a result, we need to find a practical way to manage these models, to test these models against observations, and to tell observers we don't want this model because it doesn't fit observation. So, facing such a task, what is the most practical thing that we can do? In my opinion, we should try to separate all these class of models into two categories. One is lambda CDM, the other is non-lambda CDM. So all the non-standard models, basically. The reason is that if you look at these non-standard models, I mean, when people propose a new model, they would argue this model is motivated by some fundamental theory, like string theory or something else. But you should always take a pinch of salt on that, because all these models are in fact so far still phenomenological models. They are toy models, and they are not fundamental theories. And furthermore, current observational data still do not allow us to really detect the fundamental nature of the cosmic acceleration. So for that reason, I think we should treat those non-standard models as what they really are. So what are they? They are toy models. And they can represent maybe to some extent the reality. And by studying these toy models, we can test how much deviation is from lambda CDM. If there's a deviation from lambda CDM, good. Then we know that lambda is not the answer, and we need a new theory. And if lambda CDM is confirmed to very high accuracy, that's good as well, because we know that, okay, now GR has been tested on cosmological scales for the first time. And previously, it has only been tested on small scales. So this will be a major breakthrough as well. So the question is, if you just want to say how much deviation from lambda CDM is allowed by data, why don't you just say, I want to constrain what is the difference of the, for example, halo number from GR prediction is allowed, without specifying any theory? The answer is that you can't do this, because if you change the prediction of a theory, its prediction on the halo number, then it is very likely that you are changing other things as well, like the clustering of galaxies, the CMB, BO, and so on. So you have to have a consistent framework to study all these changes simultaneously, and for that you need theories. And the question is, given that we have so many non-standard models, is it necessary or practical to study all of them in equal details? And we have a lambda CDM model, and this model has been studied again and again by different groups, different people, and using different technicals on different aspects. So it has been studied in great detail. Do we need to study all these non-standard models in equal details? The answer is, of course, no, because it is not practical. There are so many of them. And also, it is probably not necessary either, because some of these models, actually many of them, they share very similar properties, very similar behaviors, similar predictions on various cosmological observables. So if we can group them and study them together, then probably we can find easier and more practical ways to constrain such models. So this brings us to what we normally use in studies like this, and I call it a parametrization. So what is a parametrization? A parametrization is very simple. Basically, you look at all these models, and you find that, okay, this subgroup of models have similar properties. I can use some parameter to describe their properties, and then I make predictions by varying these parameters and compare with data to constrain those parameters. And if you can constrain those parameters to such extent that the model deviates from the, lambda CDM very, very tinily, then you can probably make a judgment saying that, okay, deviations from lambda CDM in this possible way is not viable. So I'll give you some simple examples of how parameterization works. And this first example is, I think, probably many of us are familiar with. This is what people use when they describe dark energy equation of state parameter W. And if you are not familiar with this, just remember that from the Friedman equation, you have seen that, the acceleration of the universe depends on the energy density and the pressure of the matter contains inside it. So if you have a dark energy, you need to specify its energy density, you need to specify its pressure. And the ratio of these two is what we call W, equation of state. In the case of a lambda CDM, a cosmological constant, W is -1, which means that pressure is minus the density for cosmological constant. But if you want to have a more generic description of W, this is one possibility. So here you have two parameters, W0 and W1, that describe the time evolution of the equation of state parameter. So unlike lambda, this is no longer -1. This can be deviating from -1. But of course, if you choose W0 to be -1 and W1 to be 0, then this will go back to lambda CDM, which is nice because this means that this parameterization has a proper lambda CDM limit. And by constraining these two parameters, W0 and W1, you can say, okay, these two parameters cannot deviate from -1, 0 significantly. So that means that the reality cannot be too far from a lambda. A second example of parameterization is this. So this is what people use in modified gravity theories or theories with interactions between dark energy and dark matter. I'll go to some of these theories later. So what these theories have in common is a time and space-dependent gravitational constant. And that means that G, the Newton constant, is no longer a constant. It depends on time and it depends on K. So this is one example of the parameterization. It has one parameter M, which is shown in red. And A here is the scale factor and K is the wave number of the length scale that you consider. So you can say that with this parameterization, at very early times when A is close to 0, this factor is 1, so you go back to the standard gravity. But at late times, and especially on small scales where K is big, then you can neglect this term so that this G becomes 1/3 larger than the standard gravity prediction. So this is one possibility. And then you are saying that, okay, I have this parameter M, I can, hello?
This parameter M has a meaning, a physical meaning?
It has,
some mass?
yes, it has mass dimension 1. Actually, so this modification of Newton constant comes from a new force that is mediated by some sort of scalar field. I'll come to that later. And this scalar field has a mass, and that is the scalar field, that is the scalar field mass.
Would it be valid for all scales? Or, I mean, is this approximation more accurate at smaller, larger scales?
Sorry?
This function, would it be valid for all scales, or do you think it would be more accurate at different smaller or larger scales?
So it's only on, in most cases, it's only valid on large scales. And if you go to small scales, you need to think of other ways to parameterize this.
So in linear scales?
Yes, on linear scales, that's right. So I'll come to the limitation of the parameterization method later. And a third example of parameterization is probably more complicated. And this works for linear perturbation level. So let's say you have a new field, maybe a scalar field. You want to derive the perturbation equations We have seen perturbation equations in Salman's talk. You want to derive the perturbation equations in this new theory. And so without being given a Lagrangian, it's probably difficult to derive the perturbation equation. However, that's one way to do it. And this is if you have knowledge, prior knowledge of what is the matter contained, what is the basic properties that you have for this field. Then if you also assume that the theory restricts some general symmetry, such as general covariance, like general relativity, then you can pretty much fix the functional form of the perturbation equations. You don't fix everything. You still leave some freedom for parameters, but the functional forms of the perturbation equations can be fixed. And then you can constrain the parameters that are left over using data. So this is more complicated. I'm not going to any detail about this. If you are interested, you can search the literature or let me know. So there are many different ways to parameterize dark energy. Unfortunately, most of them are not ideal. They are not perfect. And the reason is that parameterization is generally a trade-off between being sufficiently generic so that your parameterization can cover a lot of theories, a lot of models, and being reasonably faithful so that you can still tune some parameters to distinguish the different possibilities within the same parameterization.
I have a question with your previous slide. Models in general, the parameterization doesn't respect general covariance. Is that what you meant?
Now you assume that this general covariance is a fundamental property. This holds true in most theories for dark energy and modified gravity that I know.
The whole theory.
Yes.
The parameterization doesn't respect general covariance.
It does. I mean, this is a fundamental assumption. If you assume this, then you can fix your parameterization. So this is getting something out of thin air, out of nothing. You know nothing about basically what is the theory itself, but by just assuming this general covariance and some other simple assumptions, you can fix the functional form of the perturbation equations. And that is why this can be very powerful, but it has its own limitations because there are so many parameters in this.
I think they're not really parameters, they're free functions.
But these free functions, you need parameters to describe them.
Right, but I mean, it's much worse than free parameters.
Of course, yes. That is why this is powerful.
And we have infinite degrees of freedom.
Yes. So yeah, parameterization method is a trade-off being sufficiently generic and sufficiently faithful. So you can't have one parameterization that you hope to describe all theories that are in the market. So what in practice we can do is that we can, we have experience in studying all these different theories. And we know that, for example, models A, B, C have similar properties, D, E, F have similar properties. Then we can try to first subdivide models into different categories and then use parameterizations that describe each category well. So here is one example. F4 gravity. I believe that if you read archive daily, you see this name quite often. And this is actually one of the most popular modified gravity models. It's not like this is a fundamental model or this is people believe that this is a true model. So from my perspective, I like this model. Why? Because it is very generic. So here I give you an example of the model prediction by this model on the halo mass function. So if you haven't got to this stage, a halo mass function basically describes the number of dark matter halos as a function of the halo's mass. And halo is basically simulation equivalent, simulation counterpart of a galaxy cluster or galaxy group in observations. So here I'm varying the parameter of this F4 gravity model from this panel to this panel and to this panel. And on the vertical axis, I'm showing the relative enhancement of the halo mass function as a function of halo mass at two different redshifts, redshift 0 for solid line and redshift 0.5 for the dashed line. So you can see that these three panels, they are the same model, but they look very qualitatively different. And the point I want to talk about here is that by varying this parameter, used in this model, you can get a range, a wide range of qualitatively different behavior of the model. And these qualitative different behaviors have been seen in many other classes of models. Okay? And that means by studying this model alone, you can use your conclusion, you can generalize your conclusion to say something about many classes of other models. And that is why this approach can be useful. Again, I don't believe this is the correct model. I don't believe this is a true model, but I like it.
This is the Husavitsky model?
It doesn't matter. Husavitsky is just one example. You can have, for example, Starobinsky model or some other model proposed by other people, and they are qualitatively similar.
But the computations there were for a particular model.
Sorry?
The plots there were for a particular model.
Yes, that's right. The parameter is for this specific model, but a different model may have a slightly different parameterization. But
the same behavior.
Yes, actually they can be parameterized in a unified way, but I don't have time to talk about that here. We can talk later if you like. So for the rest of this talk, I'll focus on what is known as a scalar field. And this is a new matter species which is often a candidate for dark energy models. So this is so far the most popular candidate for dark energy models. And that is why I focus on here. So what is a scalar field? We don't really have a real life counterpart of this. I mean, you can think the density field is a scalar field because